All right, so we're still plugging away at examples of solving trigonometric equations. So here's another one. We're solving an equation that doesn't look that complicated, but it involves a cosecant, where most of the equations we've dealt with have been sines and cosines. You know, kind of our favorite trigonometric functions are sines and cosines, because those are the ones that we seem to encounter the most. We've memorized the unit circle for those. But a trigonometric equation can involve any of the trig functions, any of the 6. So it's good to practice with this a little bit too. This is another equation that resembles a linear equation from algebra. So I would solve it again by looking at isolating the trigonometric function that's appearing, cosecant of x. I can do this by subtracting 1 from both sides, so 6 cosecant of x equals, that would be 9 on that side, 10 minus 1, and then divide both sides by 6. Cosecant of x equals 9 over 6, which simplifies to 3/2. Okay? Now from here, if I wanted to solve this, I don't know the cosecant or the values of cosecant from my unit circle all that well. I don't have those memorized. So I think I would prefer to put this in more familiar terms. I know that the cosecant function is the reciprocal of the sine function. So I can evaluate this by taking the reciprocal of both sides. The reciprocal of cosecant of x is sine of x, and the reciprocal of 3/2 is 2/3. Okay, so far we're off to a good start. But then I kind of encounter another issue here. First of all, sine of x equals 2/3. This is not a number that I'm remembering or I'm familiar with from my unit circle. I would be able to do root 2 over 2 or root 3 over 2 or 1/2 or something like that, but 2/3 is not a familiar value. It has a solution because remember the range of the sine function is the interval from -1 to 1. So that means there has to be some value of x that I could plug in that would work here, but I don't know it off the top of my head. So this is one instance where we need that inverse sine function. Now, one solution to this, if I take the inverse sine of both sides, would be the inverse sine of 2/3. And I could plug that into a calculator and get a decimal or something. I'm going to leave it in this form though, because this is like an exact answer. It's like leaving something in radical form instead of plugging that into a calculator. But I am expecting there to be more than one solution to this. So this does not seem like enough. Now you may have also noticed the interval that we're solving this on is the interval from 0 to 4 pi. So that means we have to consider 2 revolutions around the unit circle, since that's what 4 pi would be. But we're going to deal with that at the very end. So what I'm going to do is think about my unit circle for a moment. And I'm going to think about my inverse sine function as well. What do I know about the inverse sine? If this is my unit circle, first of all, I'm taking the inverse sine of a positive number. And the inverse sine function only gives me solutions between -pi/2 and +pi/2. And if it's a positive number that I'm taking the inverse sine of, that must mean I'm looking at an angle in the first quadrant. So let's suppose that inverse sine of pi or 2 over 3, 2/3, is this angle right here. Okay? Let me call that, I'm going to call it theta for a moment. What I'm looking for now is a solution to this original equation. So sine of x equals 2/3, or this. Or sorry, this is one solution. A solution to this that's different from this guy. Remember what the sine function does. It looks at the unit circle, takes an angle, and gives me the y-coordinate of the point on the unit circle corresponding to that angle. So the y-coordinate of this point here would be the inverse sine of 2/3. Is there another point on the unit circle that has the same y-coordinate as this one? Yes. If I draw a horizontal line through that, taking me into the second quadrant, that point right there would have to have the same y-coordinate as this point. So what angle does that correspond to? Well, hopefully you can kind of see from the symmetry of this thing. And I can construct a good geometric argument for this, but I think it's pretty clear, even just intuitively. This angle right here would have to also be theta. You can sort of see that symmetry there. Remember, that angle is not the angle that represents this point on the unit circle. What I need is this angle right here, right? I need the angle in standard position from the positive x-axis to this radius. Well, I know that the x-axis itself can be thought of as a 180 degree angle, or an angle of pi. But if I take the entire, this entire pi radians and then subtract theta to backtrack, that would leave me with this angle right here. So that angle right there is pi minus theta. And that would represent the second solution within one revolution around the unit circle. So if I already have a solution, x equals the inverse sine of 2/3, then pi minus that solution would have to also be a solution to this equation. Okay? Now, how do I get the other solutions? Because so far, I'm only looking at 2 points within one revolution of my unit circle. And this interval is telling me that I need to look for 2 revolutions. Look through 2 revolutions around my unit circle. Well, basically all that means is that I'm looking for 2 angles that are coterminal to these that would lie in my second revolution around that unit circle. So if I start at this point, to get to that next coterminal angle, I would just be adding 2 pi to this solution. X equals my previous solution, sine inverse of 2/3 plus 2 pi. That would be the angle that's coterminal to this after adding one more revolution. Now if I start at this guy, I could do the same thing. Add 2 pi to that to get me a coterminal angle that's in the second quadrant, but it's what I get after adding, that extra revolution. There's already a pi here. If I add another 2 pi to this, that takes me up to 3 pi. So x is equal to 3 pi minus the inverse sine of 2/3. This would represent all 4 solutions that I would get from those 2 revolutions around the unit circle. Now this may seem like a funky solution because normally your inclination is to, again, plug something into a calculator. And if you look in the back of your book, I think for some of the answers where you have to do this, it actually does give you decimal approximations. Even if the book does that, I don't want you to do that. This would be considered an exact answer. Plugging it into a calculator is going to give you a decimal that's already been rounded. That's an inexact solution. That's a rounded solution. I want to see this if the solution requires an inverse trig function. Okay, let's move on to another one. I want to solve this equation. 2 sine squared of x plus sine of x equals 0. Okay, so this is starting to resemble kind of a polynomial. If I were to rewrite sine of x as u, if I said u equals sine of x, then I could rewrite this equation in the form 2u squared plus u equals 0. That looks like a polynomial equation. Polynomial equations you don't solve the same way as linear equations. As we saw at the very beginning when we took a look at those 2 algebraic equations. Linear equations, you isolate a variable. Polynomial equations, what you're typically doing is trying to factor those and then use the zero product property. So this is just to show you that it's a polynomial equation, but I'm not actually going to use this form. I'm going to work directly with what I have. Can I factor this? Well, there's 2 terms in this left-hand side of the equation, and both of them have a factor of sine. So I could factor a sine out. That would look like this. Sine of x times 2 sine of x plus 1 equals 0. Now the point of factoring when solving equations of this type is to factor one side so it looks like a product of 2 or more things, and then the other side should equal 0. Because my zero product property says that if I have a product of one thing times another thing that equals 0, then either this thing or that thing had to have equaled 0 for that to be true. So I can individually set both factors, sine of x equal to 0, or 2 sine of x plus 1. I can set that equal to 0. Okay, sine of x. When is sine of x equal to 0? Well, notice I'm looking for general solutions here. So sine of x is equal to 0 when x, in one revolution around the unit circle, when x is equal to 0 or x is equal to pi. When is 2 sine of x equal to, or 2 sine of x plus 1 equal to 0? Subtracting 1 and dividing both sides by 2 gives me sine of x equals negative 1/2. And we've actually already solved this equation. This has a couple of solutions. X is equal to, what was it? It was 7 pi over 6, and x was equal to 11 pi over 6. Now we do want general solutions for this because it doesn't say to solve on an interval. But I want to point something out that's kind of unique about these two solutions here. Even though I could say plus 2 pi k and plus 2 pi k, which would be correct, there would be overlap between the, or sorry, let me back that up. There's a way of consolidating these into one solution. So here's what I mean. Where is the angle 0 and where is the angle pi? Let me draw a little unit circle right here. 0 is right there, and pi is right there. And notice, if I started at 0 and just added pi to that, it would take me to this solution. Then if I added pi to that, it would get me to this solution. And then if I added pi to that, it would get me that one. And I would keep going back and forth between these 2 points, finding angles that are coterminal to either of these. So actually a better way of writing our solution set is to write x equals 0 plus pi k instead of 2 pi k. 0 doesn't even need to be there. I can actually just write pi k. So in other words, all multiples of pi. 0 is a multiple of pi because it's 0 times pi. Pi is a multiple of pi because it's 1 times pi. And then every other multiple of pi just bounces me back and forth between these two solutions. So again, even though this produced 2 separate solutions, when writing the general solution, I don't need to say plus 2 pi k to each of these. I can consolidate everything by just putting it in this form here, x equals pi k, because that includes all multiples of 2 pi plus these solutions. I can't do that with these two guys because these two guys don't have that angle of pi between them. So for those, I do need to write x equals 7 pi over 6 plus 2 pi k, and x equals 11 pi over 6 plus 2 pi k. This would be the general solution to that equation. Okay? Still have, I think, about 5 more examples I want to look at. So again, lots of variety in these things. This is the first example that we're encountering where we have a mix of 2 different types of trigonometric functions in our equation. When you encounter this, you generally want to try and get it down to just one type of trigonometric function. So I have a sine here and a cosine here, technically a cosine squared. I would like to only work in terms of sines or only work in terms of cosines. I don't like having 2 different types. And this is where your identities start to become useful. I know from my Pythagorean identity that cosine squared of x is the same thing as 1 minus sine squared of x. And if I were to rewrite this as 5 minus 2 times, you have to have parentheses here, 2 times 1 minus sine squared of x equals 5 sine of x. Now everything is in terms of sines instead of having a mix of sines and cosines. And from here I can solve this using some algebra. So 5 minus, I have to distribute my negative 2 in, so that becomes negative 2 plus 2 sine squared of x. Okay? Now what I'm going to do, that's equal to 5 sine of x. I'm going to move some things around because even though everything is in terms of sine, I do have a sine of x here and a sine squared of x here. So it's starting to look kind of like one of those polynomials. Let's try using my zero product property. In order to do that, everything needs to be moved over to one side so that I get a cosine or 0 on one side of my equation. I'm also going to rearrange some terms here. So 2 sine squared of x, let me put that first. 2 sine squared of x. I know that I'm going to have to subtract 5 sine of x over to the left, which is going to give me minus 5 sine of x over here. And then 5 minus 2, that would be 3. So let me put that 3 last. That's kind of the standard form of a polynomial. Next thing I'm trying to do is factor this polynomial right here. Now notice, if I take sine of x and call it u again, to kind of make that variable substitution, this equation can be written as 2u squared minus 5u plus 3 equals 0. And this is a polynomial, specifically a quadratic, with a leading coefficient of 2. There's a specific way that you can go about factoring these things that you learn in algebra, and I actually teach this in a way that not everybody teaches, so it might be worth looking at that. You multiply your leading coefficient in your constant term, 2 times 3, that's 6. And then you take the linear coefficient, which is this guy, this -5, and you put that down here. Okay, the next thing I'm doing is I'm looking for two numbers that multiply to 6 but add up to -5. It doesn't take a whole lot of work to see that that would be -2 and -3. Okay, now here's where this takes maybe a different turn depending on who you or where you learned this technique from. What I do is I take these two numbers and I create fractions out of them. So these two numbers that I just found are going to be the numerators of these fractions. The denominators of these fractions are going to be my leading coefficient on this quadratic, 2. Like that. Now, if either of those fractions can be simplified, I would simplify them. -2 over 2 simplifies to -1 over 1. And notice, normally you would want to just write -1, but I'm intentionally keeping this as a fraction because I'm going to use both my numerator and denominator in this process. I'm going to take my variable, in this case it was a u, and put that down next to the number in my denominator. That's going to tell me how this factors. 1u minus 1, or I could also just write u minus 1. 2u minus 3. 2u minus 3. This is how this quadratic factors. And if you want to check it, you can verify by multiplying it out. You'll end up with this. Okay? It's a very, very handy technique for factoring quadratics with a leading coefficient of something other than 1. I'm not really dealing with u's, though. I'm dealing with sines. So let me put that in terms of sine of x. Sine of x minus 1. 2 sine of x minus 3 equals 0. Remember what we do from here. We want to use our zero product property. So this equals 0 or this equals 0. Sine of x minus 1 equals 0. Or 2 sine of x minus 3 equals 0. How can we get either of these to equal 0? Well, let's isolate the sign in each one. Sine of x equals 1, or sine of x, adding a 3 and then dividing by 2 gives me 3/2. Okay? And this is where I now resort to my unit circle to try to search for solutions. But one of these hopefully should set up a red flag for you. This has no solution. Sine of x can never equal 3/2. And how do we know that? The range of the sine function, again, is the closed interval from -1 to +1, meaning sine can only ever give me answers or outputs that are between -1 and +1 or equal to -1 and +1. Never greater than 1. 3/2 is a number that's greater than 1, so this would never end up with any solution. I can just discard that because it gives me no solutions. I'm only now focusing on sine of x equals 1. I believe we've solved this one already. This only has a solution within one revolution of the unit circle when x is equal to pi over 2. Actually, we didn't solve this exact equation, but one very similar to it. We're not asked to solve on an interval, so I need my general solution. Plus 2 pi. Okay, that would be the solution to the original equation. Notice there was a lot more steps involved in this one than what we started with, and that's intentional. We're kind of gradually building up to more and more difficult problems. Okay, so nothing fancy going on there, but kind of bringing in some of our algebra knowledge to solve a problem like that. All right, next example. I want to solve cosine of 2x equals 1/2. And this time we're solving on an interval, 0 to 2 pi. Now, there are a couple of approaches I could take. One thing I could do is try to use a double angle formula to rewrite the left-hand side of this equation. And that is a valid approach. I could use that. Cosine has 3 different double angle formulas, as we learned in 9.3. So you'd have to pick one that seems like, whatever the best choice would be, and then go with that. I'm going to show you a different approach, though, that I think is actually better for a problem like this. I'm not going to use a double angle formula here. Instead, what I'm going to do is notice that I already have a nice number on the right-hand side here, because 1/2 is something that shows up on the unit circle. Cosine of, for example, pi over 3 would be equal to 1/2. So if I can get this thing on the inside here to become pi over 3, then cosine of that would give me 1/2. That would give me one of the solutions to this. So what I'm going to do, before I even do that, is I'm going to rewrite this interval in inequality form. So again, to say that we're solving on the interval 0 to 2 pi is to say that we're looking for values of x such that x is greater than or equal to 0 and less than 2 pi. This interval is the same thing, this inequality notation is telling me the same thing about x as this interval. So it's an alternative way of writing that. The reason I'm doing this is because I have an angle in my cosine function that's not just x. If it were just x, it would match this. Instead, it's 2x. So I want to think of it this way. If x is between 0 and 2 pi, then where is 2x? I can determine that by multiplying through this inequality by 2. If I multiply everything by 2, I get 2x is less than or equal to 0, which is less than 4 pi, because I multiplied that by 2. Now what does that tell me? Well, that tells me that if my angle looks like a 2x, as I search for solutions, I'm actually looking through 2 revolutions around my unit circle. Angles between 0 and 4 pi. That's what I'm looking for. So what angles would work? Well, we already said if cosine of 2x is equal to, if the angle on the inside here is equal to pi over 3, cosine of pi over 3 is equal to 1/2. But the angle on the inside here is not an x, it's a 2x. So if 2x is equal to pi over 3, that would give me one solution to this. Where else would cosine give me a 1/2? In the fourth quadrant, where cosine is also positive, 2x equals 5 pi over 3 is a valid solution. But these are the 2 solutions that I would get within that first revolution around the unit circle. Remember, this tells me that I need to go through my second revolution and continue searching for solutions. So that would be like finding angles coterminal to each of these, which are within that second revolution around the unit circle. I can find those solutions by simply adding 2 pi to each one of these. 2x equals, that's pi over 3, 5 pi over 3. What is pi over 3 plus 2 pi? That would be 7 pi over 3. And then finally, 2x equals 5 pi over 3 plus 2 pi. That would be 11 pi over 3. Okay? Now, even though I wrote this out in kind of that long form, there's actually kind of a more compact way of writing this. So I did this once doing this vertical notation, but actually this is the same thing as if I were to write this. 2x equals pi over 3, comma, 5 pi over 3, comma, 7 pi over 3, comma, 11 pi over 3. This notation is more efficient because everything is arranged in a row and I don't have to write 2x 4 different times. Now remember, we're not solving for 2x, we're trying to solve for x. So now, if I want the solutions for x, I would just divide everything by this 2 here. X is equal to pi over 3 divided by 2 would be pi over 6. I would also have here 5 pi over 6, 7 pi over 6, 11 pi over 6. And if you notice, something interesting happened. Even though these angles here were between 0 and 4 pi, after dividing everything by 2, all of my solutions are from the original interval. They're all between 0 and 2 pi, where they belong. Okay, so this captured all of my solutions without having to resort to a double angle formula or any other fancy technique. That should do it for this second video.